I mean, sometimes I wonder if I would have stayed in science if I knew that I could be doing these experiments.
Motivates me to get more involved. I'm like, you tell me I professionally can scare crabs?
Yeah, no, exactly. Like, if I had known that this is what I could have been doing with my time instead, like, I'd still be a scientist.
Let me just preface this. Like, the name of the game is absurd questions here, but still answerable in some way, right? Like, they can't be semantically nonsensical. It has to be a question that I can attempt to answer. And this one, like, another one of those, like, every word in that sentence was a surprise. This question comes from Sai, and it is: how long would it take to complete a playthrough of Doom on a computer made entirely out of crabs?
Wow. And so much to unpack there.
Yeah.
Sai, goes in a little more depth. He says, it would take an estimated 600 years to complete the game on the MIT E.coli computer, and I was reminded of the 16 billion crabs article from a few years ago. That combination just got me curious. And all of this, look, I'm very online, okay? I'm very online. All of this was a surprise to me.
Yeah.
I'm like, what is he talking
I've never heard
about?
of the MIT E. coli computer, and now I feel like such a bad bioengineer.
And I've never heard. I like that he just is like, oh, and the 16 billion crabs article. So you know it. Everybody knows it.
What is he talking about? So, first of all, Sai, congratulations on defeating me in Who's More Online. Like, you win this one. But let me fill you in. Okay, we'll work backwards. So starting with the MIT
Julian,
E. coli.
What is Doom?
Yes. Okay, I guess we should start there.
Yeah, I actually need this because I
This is important. You're right.
About games.
You're right.
Yeah, what is Doom?
I assume everybody's as much of a nerd as I am, but so I'll explain. Doom was a seminal landmark touchstone game. It's basically the invention of the first-person shooter genre as we know it. It came out in 1993 for PC and I think Mac. And famously, it was a game that you could just like share over, the internet and download or like burn it onto a CD and play it. You've probably, even if you've never played it, you've probably seen like what it looks like at some point. It's just like floating weird monsters.
Yeah, some of them are like D&D influenced, right?
Yeah. The premise of the game is a portal to hell has opened on Mars. And you, the unnamed protagonist, colloquially known as Doom Guy, are the only one who can stop it. And the game's famous for having like the gun coming right out of the middle of the screen, so it's kind of like you have a third arm in your chest. And anyway,
it just seems really easy to beat this. Like, you just don't go to Mars. Like,
hey, there you go. Leave Mars alone.
Yeah.
No,
it's fine.
We shouldn't be there anyway.
Yeah.
You hearing that?
Yeah.
So to make matters more confusing, a remake of it came out in 2016. Well, like a totally reimagining, and it's super good. But they also just called it Doom. So I'm going to assume that Sai is talking about the 1993 version of the game that involved a lot less computing power, which also makes my life easier for reasons I'll get into in a minute.
And just to sidebar here, Julian, Wolfenstein people want a word with you about it being the first-person shooter. Jeez. Wow.
Okay. I'm just gonna say, like, not necessarily the first, but like popularizing first-person shooter genre. I would say it's like the reason for it.
I see.
Okay, so now that we're all on the same page on what is Doom, let's talk about that MIT E. coli computer.
Yeah.
From what I could find, in February 2024, there was actually a grad student, Lauren Ramlin, programmed Doom to run on a display that was made of, instead of, like pixels made of LEDs and stuff, E. coli cells.
Okay.
Yeah.
So the computer itself is still a computer.
Yes, it's still an electronic computer, but the display it's outputting to is like a grid of cells, like a 32 by 48 grid, and then these E. coli cells can fluoresce when they're, exposed to a certain signal.
Yeah.
Right? Like a biological signal. And then like the computer will basically, to each individual pixel made of E. coli in this grid, tell it to either light up or not light up, and you can form very grainy images on it.
Yeah.
Right?
Do you know, is that part of why it takes so long to beat the game?
Now, I couldn't find any details on that. Here's what my assumption is, and that is that the refresh rate of this monitor made of living biological cells is very, very low.
Yeah.
Movies, moving images, video games, right? It's all an illusion.
Yeah.
They are still images that are presented to us so quickly that it tricks our brains into thinking that it's actually something moving, right? When it's just a series of still images. And it has to go fast enough in order for that illusion to happen. Otherwise, it looks like a slideshow, right? So movies typically are at about 24 frames per second if they're on film. Digital, 30 frames per second. If you're a big film geek, 29.97 frames per second, fine. Video games, you want typically a higher frame rate because the action's smoother, and it also results in like less input lag. Like literally the image on the screen isn't there for as long, so when you decide to like click a button, you have more accurate information when you're making a decision, that sort of thing. Games, you want typically a minimum of 60 frames per second. So my assumption is the E. coli display frame rate is really, really low.
Yeah.
And so if you were to try and actually play through it at this low frame rate, like a slideshow, it would take a while. I think that's where Sai is getting the 600-year estimate, because I couldn't find that.
Yeah.
Now, let's talk about a crab computer.
Yeah, tell me about crabs. That's a delicious computer.
So this is not the same as a display made of E. coli, right? Because that's just like taking the output from some electronics and just showing you the results.
Yeah.
Not so with the crab computer, okay? In 2012, scientists from the Kobe University, along with another scientist based in the UK, they came up with a actual method of performing computations with crabs. And it's basically the biological analog of what your computer is doing with electricity.
How?
Right?
How? No. How?
Okay. So I'm not the biggest computer science guy. I know I look like I really should be, but like to me, it's all kind of magic still.
Yeah.
But I'll explain as best I can, right? And that I think everybody knows about how your computer uses zeros and ones to represent information, right? At a basic level. That's binary codes,
on,
right?
Off.
And the reason we use binary in computers, right, like this base 2 system instead of base 10, like we're used to counting and representing numbers and stuff, is because, exactly like you said, Trace, we can represent a 1 or a 0 with an on or an off switch, right? So these transistors that are in the microchips that power your computer, they're the brains of your computer, right? They're made up of millions to billions of these little transistors, and these transistors either allow electricity flow through, so they're on, and that's a 1, or they block it, they're off, and that's a 0. That's the most fundamental level. The next level up is when we start applying logic gates to these transistors, right? So you can start performing calculations and manipulating the information coming through if you start applying rules to it. So the most simple gate in your computer is a NOT gate, right? And that involves just one input, like one transistor. If the transistor is in the on position, when that signal goes through the NOT gate will flip it to the off position. And vice versa. If the transistor is off, the signal going through the NOT gate will output on, coming out, right? So it's just an opposite.
Yeah.
Then there are gates that use 2 or more transistors, right? So you have OR gates where you have like transistor A, transistor B. If either of those is on, then the gate outputs an on signal. If both of them are on, it outputs an on signal. If neither of them are on, then it does not output an on signal. It's off. You've got and, which is where both signals, both transistors have to be on. Any other combination, it doesn't output an on signal. And then you can further combine these. You can combine an and gate with a not gate to create a NAND. You can combine it with a not and or, you get NOR. And then it gets even more complicated. You can combine these even further and have exclusive and, exclusive or. And so these 7 logical functions are basically everything that your computer needs in order to perform calculations and ultimately run programs and just do stuff with math.
Let us talk to each other over the internet.
And share cat videos, ultimately. The most important thing, right? Like, these scientists in Japan, apparently, they were on an island doing field research, a small island. I know Japan is itself a bunch of islands, but it was a small island. I've got to be aware of pedantic people who are going to pop up in my messages, right? But they were at Funarua Bay in Iriomoto Island. I'm sure I butchered all of that. And they were at these lagoons, and they noticed that, like, there are these little soldier crabs, tiny little blue guys. They're really cute. And when, the water comes in, they come out from their little burrows, and they scurry around in big groups, and they can be, like, hundreds to thousands of these little soldier crabs running around. And they were observing the behavior, and they noticed that, like, soldier crabs in the middle of the little group, they like to be in the middle of the group. They're like, okay, we're going to stick around right here. It's safe, like we're in a herd. And then the ones on the edge of the group, instead of being like, let's go back to the middle where it's safe, they're like, we're going this way, everybody. And they just kind of lead a charge, like a bunch of little soldiers, like just running around. And then the waves and the natural swarming behavior, they kind of get engulfed in the middle. And then the former leaders kind of become little followers. And the new ones on the edge are like, all right, everybody follow me this way. And so they go like running off in that new direction. They looked at this, and being the fantastical nerds that they are, they were like, we can make a computer out of this.
People are so nerdy. It's
they're so inquisitive.
Thing. I love it.
They're like, right.
Yeah, I don't think I've ever looked at crabs and thought like, computer.
I can make that a computer.
How can I use this?
I thought I can make that lunch.
Yeah.
That's it. And even that's weird if you think about it. Anyway.
Out of the crab?
Yeah.
So they looked at these crabs, right? They're like, okay, first, let's see if we can, like, model this behavior in some way, right? If we can come up with a mathematical description that accurately kind of imitates how these crabs move around. And they accomplished that in their paper, right? The whole, like, leader versus follower depending on position. They mathed that out. And then they were like, okay, well, let's say we design a series of hallways for groups of crabs to travel down, okay? If we arrange these hallways in a certain way, can these hallways function as these logical gates that your computer uses to process information? Okay, so I've shared an image from the study in our chat, and Deboki, do you see it? What is that? Can you describe that?
I mean, I can certainly try. Okay, so my first thought was that this looked like it was like out of a children's book. Like we're reading some book about like kids who are stuck in a maze, like a haunted maze, and they're just like in a mass and walking around. So I think what we're watching are hallways shaped like little X's on this board, and there are little masses of black dots that I'm assuming are supposed to be the crabs going through these hallways. And there are red arrows indicating where they're going, and that is the computer.
Yeah, that's it. So specifically, this is an image of this hypothesized AND gate, right? So you can see it's like basically an X shape with like another fifth passage going straight up from the middle. And the idea is you've got your little groups of crabs, right? So an AND gate, to refresh your memory from a minute ago, is when you take two inputs, If both of them are off, it outputs off. If only one of them is on, it still outputs off. So both of them have to be on in order to output on. So the idea here is the crabs themselves, the group of like 20 crabs, represents an on signal. And they march together down this hallway. And when they come to the intersection, if they don't encounter another group of crabs, they keep marching off diagonally, right? So that still outputs off to this gate. Or if there's no crabs there, obviously no crabs go through. But if two groups of crabs come to this intersection simultaneously, instead of going off diagonally, they come together and merge, and they go straight up through that central fifth channel, and that is outputting on. So that is a logical AND gate.
Got it.
Yeah.
Wow.
And they just know the crabs are going to do this based on their behavior.
Right.
Huh.
But then...
My brain hurts.
Wait. It's not purely theoretical. They did it with actual crabs.
Oh, no.
Yes. So they modeled this behavior. So they've constructed the different kinds of gates, right? Like an OR gate is much simpler. It's just like basically a Y shape, you know? And then I guess they must have a NOT gate. I didn't see that in the study. But they actually built like an AND gate with like little acrylic walls, and they have like little starting areas for two groups of 20 crabs, and then like a little cardboard, like orange piece of cardboard behind where the crabs start. And the idea is they open the little gate, and then if they want to motivate the crabs to move, they like flip up the little orange card so it casts a shadow over the crabs, and the crabs think, a bird, and they start scurrying. And then they tested how frequently they went down like the correct channel that they should go down to make the logical operation happen. And in a lot of instances, they did fairly well. Like if it was only one group of crabs, they would go down the correct like channel that would output like not on in the AND gate, like about 80% of the time. But when two groups came together, they went down the correct output channel that would output like on about 50% of the time.
Yeah,
like
okay.
some of them would get lost.
That's
and so
a lot
it
of error
introduced,
correction.
Like, signal noise. Right. But the paper is like so optimistic.
Yeah.
They're like, oh yeah, but it's still in the early stages of development. Like they're going to continue this line of like,
how
we're gonna
big
design
are these like these structures?
They're small. I mean, the crabs themselves, the soldier crabs, I mean, they can fit really easily in the palm of your hand. They're small little guys. So to get like a group of 20 of them together, it doesn't have to be very big. So the structure itself like fits on a tabletop basically. I have the PDF of the
because originally I was
study.
like in my head it was like big crabs. It was like Squid Game like arena style, like really big. But it's a relief that it's like contained.
What?
Yeah, there's a little ethical statement at the end. Like we didn't hurt any crabs. Like,
I mean, sometimes I wonder if I would have stayed in science if I knew that I could be doing these
this
experiments.
Motivates me to get more involved. I'm like, you tell me I professionally can scare crabs?
Yeah,
like,
no, exactly. Like if I had known that this is what I could have been doing with my time instead, like, I'd still be a scientist.
Absolutely.
That's amazing.
Absolutely.
That's
You
so
had no
funny.
idea this was even allowed, but it is.
No,
apparently.
and it's actually this like actually ties into one of my lab mates. His work was creating these kind of logic gates, but in like in human cells, and so getting them kind of like the E.coli to like light up under certain conditions. And he created this incredible array of like all of these logic gates, and it took like years, and absolutely zero crabs were involved. So like I don't like I'm like we could have been doing this, Ben. Like we could have been
crabs. Yeah,
my
but
God, so
the fundamentals of how computers process things, right, can be applied to other systems. It's not confined just to electricity. And yeah, there are possible applications in like basically biomedical,
Cool.
Making like tiny little biological machines essentially.
Yep.
Yeah. It's very, very cool stuff. But there are issues with like predictability, basically the noise in the signal.
Yeah.
And that's the problem with this crab pewter of the number of crabs that don't properly go where they should to execute the logical operation, and so it messes up like whatever you're trying to do.
Right.
So you've either got to redesign the little crab channel or have some sort of noise correction, which would involve, I'm sure, more crabs.
You'd have to run the same. As far as I know, error correction is just running the same experiment through more than one, probability.
Yeah.
So you're just like run it through 10 different gates, the same calculation, and it's like, well, 70% of the time they pick the right one, so that's probably the right one. But again, I'm not a computer science person.
On the issue of more crabs, let's get to the 16 billion crabs story that Sai alluded to.
What
Do you
is
remember
that?
the insanity of this question?
Yes.
Let's
I
make
thought
sure
this
that
was
we're
the
all...
16 billion crabs. Like,
No,
I thought we
no.
were going to find out that this
Oh,
involved 16
Deboki,
billion.
this was 40 crabs. We haven't even scratched the shell yet.
Sai, this is a question. We're still unpacking the question.
Yeah, I thought
all
I
the
was
way
on a
down.
journey, and now I'm like, I was in one place the whole time.
No, the answer's going to take 2 seconds, honestly. We're just getting through the question. So I found a story from 2021 that the headline is, "You could run Doom on 16 billion crabs."
Luckily,
it
it's
was-
a very specific number, so.
I know. So it was alluding to this study originally from 2011, and apparently somebody said, okay, well, you should need, therefore, this many crabs for a logic gate, right? They said, like, you need 8 different groups of crabs for a bit, so it's like 80 soldier crabs to run a single logic gate, and then therefore you would need, if you scale that up, 16 billion crabs to have the computing power necessary to run Doom. But I think the question is really like, at what speed are you running it, Because like, if you've ever tried to run something your computer's not cut out for, it will try. It will go through the motions of attempting to do the calculations, and it will be slow, but it will try and get through it. So I think the question of the number of crabs is how quickly do you want to do it? If you have fewer crabs, you could probably still try and do it. But the question Sai asked was about time. How long would it take? And so I had to kind of dig back to, the 90s, if we can all go back there for a minute.
Wow, there's so much neon back here.
Oh, cool. I've got a sweater tied around my waist.
Definitely. And that
That's
sweater
what I
has like a
think of
stripe on it for no reason.
Yeah.
Like a big, thick
My
one.
favorite Power Ranger.
You got it at the mall.
Yeah. Remember when brick and mortar retail existed? Those were the days.
Wow.
Yeah.
Okay. So when Doom came out in late 1993, a typical home computer would probably have like an Intel i486 chip in it, right? This is like your CPU. This is the brain of your computer. Yeah. And this is also before dedicated hardware that was meant for running computer graphics existed, right? The GPU, graphical processing unit, that was invented in like the late 90s, I think like 98 or 99, by a company, disclosure, that I've worked for called NVIDIA. So this is what, modern PCs use for graphics, because they're engineered to run calculations in parallel much more efficiently, which is good for outputting graphics, because to do 3D graphics, you have to do a ton of number crunching. But before that, in the 90s, we just ran it through the CPU, which just basically operates everything in sequence, like one after another, one calculation after the next. So it's more limited, but in the 90s for like Doom, it was fine. It was enough. 486. It has a clock speed, I'm going to estimate, of about 40 megahertz. So what that means is 40 million times every second, it does a cycle, and a cycle is switching the transistors on or off inside the chip, right? So the way that I tackled this question was thinking like, all right, a cycle is basically the time it takes for these crabs to run through a logic gate.
Yeah, that makes sense.
Yeah.
So how long does it take these crabs to traverse this gate? Well, the study doesn't say. So, except they did say when they put the crabs in their starting areas, they gave them about 2 minutes to calm down. So when they opened the gate, they didn't just like run off, you know? I'm going to assume that we're not going to do that every single time they need to run through a new gate. I'm going to assume that like it's a crab chain reaction, and once they're off and running, it's just continuous, you know, like let's just to simplify our lives. And then the question is, how long does it take their little crabby legs to scurry through this? Well, I found videos of them running along on the beach, and I just basically did a rough estimate. And I said, you know, I think it would take them about 10 seconds to get from their starting area, maybe collide with another group of crabs, and then head off down the correct hallway to perform this operation, right? This one cycle. All right. So if the CPUs that Doom would run off in 1993 were capable of 40 million cycles per second, but our crabputer can do one cycle every 10 seconds, then our crabputer is 400 million times slower than our 1993 computer.
That's slow.
You thought your 1993 computer was slow. No.
Crabputer's slow.
So let's assume you're a really dedicated gamer and you don't mind that your E.coli screen updates like super slowly with every new image based on the crabputer's computations, right? I looked up, all right, it takes Doom from 1993 actually running at a playable speed, takes a player about 5 hours to get through it, according to howlongtobeat.com, a website that I recommend if you're an adult who wants to play games but never seems to have enough time.
I was hoping you were going to do like the first-hand research. Like I looked it up.
No, it's been a while, but I'm also like really slow because I love exploring every nook and cranny.
I do too.
So, but How Long to Beat, aggregates people's times and says, okay, typically it takes people, if they're not doing the extra stuff, 5 hours. If they do a completionist run, like 9 hours, whatever. Okay, so assuming you're just trying to do the bare minimum and it would normally take 5 hours, but your computer is 400 million times slower.
Wow.
Those crabs aren't going to last.
Yeah, you're going to need to breed new crabs while also playing the game. Are there even this many crabs in the world?
It would take, apparently if it's going to take 16 billion crabs, okay, then apparently it would take 5 times 400 million is 2 billion hours to play through Doom. Which,
that's too many. That's too many hours.
I know. Yeah. Too many hours. So really, if I calculate that in years, hold on. That would take you approximately 228,310 years to play Doom. Long enough for us to get to Mars and for an actual portal to hell to open there, in my conservative estimation.
Wow.
Yes.
Julian.
But, and yes.
This was amazing.
Yeah.
This is so bizarre.
You got a definitive answer. Is that the first time we've ever had a definitive answer?
It was really straightforward. And, caveats, like I said, I'm not the biggest computer scientist guy. This was my best understanding of how this all, I think, should work, and making some assumptions on
Give it really big error bars. 200,000 years.
2,000 years.
Plus,
give or take 100K.
Give or take 100,000 years.
And several trillion crabs over their lifespan.
This is weird. This is so weird.
I love it. Long enough for the crabs to evolve into something else, and then to evolve back into crabs as everything ends up being crabs again.
True.
As we know.
Wow.
Yeah. Fantastic. Super fun. So thank you, Sai. Thank you for that sublimely weird question.
Yeah.
So
that
weird.
was incredible.